Okay, in this presentation we're going to look at how to compute a confidence interval for a Poisson random variable. Okay, so the number of claims that arise under a policy of a particular type in a year is to be modeled as a Poisson random variable with parameter lambda. Okay, a random sample of 500 such samples, that's a large sample, keep that in mind, gives rise to a total of 84 claims in 1999. Calculate a 95% confidence interval for lambda. Okay, now I'm going to sort of go through it, break it up into small chunks. Okay, the first thing I'm going to remark upon is that we still use the sort of standard structure of a confidence interval here. So the point estimate, which is our estimate for lambda, quantile, in this case we're going to use a 95% confidence interval, and it's a large sample, so I'm just going to go straight to 1.96. And then the standard error for the question, the standard error essentially. Okay, so let lambda denote the unit parameter for a unit. Sorry, that's just the parameter for a unit for one policy. Okay, and the number of claims which arise under a single policy of a particular type in a year is denoted x. Okay, now the expectation and variance of x are both, this is the basis of the normal distribution, or the Poisson distribution. Expectation equals variance equals lambda. Okay, that's common to all of these. Now we're going to use this as our point estimate, okay, and our variance, which we're going to use in standard error. So this is our point estimate straight away, point estimate. I'll just call it point. And this is going to be part of the standard error, the variance there. Okay. So our point estimate here for one policy is 0.168. We had 84 cases out of 500. So 84 divided by 500, that gives us our expected value of the number of cases that should arise for every particular policy. Okay, every policy. So 0.168 per policy. So that's lambda hat, and it's a large sample as well. So we're going to sort of say, you just sort of say this stuff every so often just to justify your approach. The sampling distribution is properly or adequately or appropriately approximated by the normal distribution. Okay. Now, this is the general structure for a standard error when you're calculating a confidence interval in the conventional sort of material where you're looking at this stuff for the first time. The sample mean, the standard error of the sample mean. Okay. Now, in this particular instance, what I'm going to do is there's two different ways of calculating it. They're not different actually, just slightly, one is slightly rephrased differently from the other. But the second one is the one I'm going to use. The square root of the variance divided by n. Okay, so that's the one I will use in this particular instance. This way of stating it. Okay, in other videos I actually will use that one as a preference. Okay, so that's how we get here. So the variance, sigma squared, is lambda hat. N is n, 500. And we have our point estimate here as well, on 1.96. This is structured exactly as I sort of started with at the start of the exercise. Point estimate plus or minus quantile times standard error. And here the standard error is the square root of the variance divided by n. Okay, so essentially that's really it now. We've actually sort of broken the back of it. So 0.168 plus or minus 1.96 times the square root of 0.168 divided by 500. Working it out, and we should get down here to this answer here. You could probably take it a little bit further and express it as 0.132 to 0.214 if something like that, if you wish. Okay, I'll just leave it as that, but you can take it that one step further just to sort of express the upper and lower bound of the limit explicitly. So I think that's everything. The key thing to remember really is, so I'm going to scribble it out, I'm going to sort of get rid of it here, but the key stuff to remember is using this stuff here. And also, you know, how to sort of determine the point estimate. Okay, and remember it's for each policy. Okay, so yeah, that's grand. We'll leave it there. Okay.